Hey everyone, this is a video lesson that I'm using in my AP Calculus AP class, and I'm putting online in case it would be helpful to others as well. There is a link to a printable set of guided notes that you can use to follow along with the problems as I go over them in the description of this video. In this section, we are going to discuss area between two curves. Let's begin with a little warm-up problem where you use a circle within a square, and you are to find the area of the shaded region. Okay, so you may remember a problem like this from geometry, right? Where what you can do to find the area of the shaded region is you can say, all right, let's find the area of the square, which area of a square is side squared. And so in this case, that would be 16 squared. Which is what, like 256? Yeah, I was right. I didn't look at my notes, I swear. I looked after. Okay, square inches. And then we can find the area of the circle, which that formula is pi r squared. So for this case, that would be pi times 8 squared, which we'll just call 64 pi square inches. And then the area of the shaded region would be what? Okay, why did we do both of these calculations? Because the area of the shaded region is the area of the square minus the area of the circle, right? You take out this area from the total area of the square to get the area of the shaded region. And we're just going to write that as 256 minus 64 pi square inches, or I do have an approximation. That is approximately 54.938 square inches. Not so bad, right? All right, so we're going to do something really similar in this section. It's just instead of working with different formulas of different shapes from geometry, we're going to work with different equations of different curves on the coordinate plane. Take a look at the new example 1. How would you find the area of this shaded region? Okay, well, we now know that we can take an integral over an interval of a function to find the area between the curve and the x-axis, right? So if we integrate from 0 to 1, that's at 1. If we integrate from 0 to 1 the square root of x, we would get all of this. We would get the area below the curve, the area between the curve and the x-axis with the square root of x. Okay, but we don't want this part right here. I'll do a different color. Okay, we don't want this part right here in our final answer. So how do we take that out? Well, that would be taking out the area of the region from 0 to 1 under or between x squared and the x-axis, right? So taking out means subtract. And so if we do the upper curve minus the lower curve in an integral, that is saying let's take this total area minus this area to get the area between the two curves. Okay, and from here we can use the fundamental theorem of calculus. We could say let's add 1 to the power, flip that, so we have a 2/3 x to the 3/2 power minus 1/3 x to the 3rd power over 0 to 1. 2/3 times 1 to the 3/2 minus 1/3 times 1. Okay, I'm just doing capital F of B minus capital F of A. 0 in for both of those x's. I'm just going to save myself some writing and say that's going to all end up being 0. And so what we have left here is 2/3 minus 1/3, which is 1/3. We got the answer. Okay, and if you were allowed to use your calculator on this, you wouldn't even have to show all of that work. You could go to your calculator and do Math 9, but keep in mind that you would need to know how to set it up first, right? That's actually the key here. in this section is understanding what is the integral that you are setting up. We assume that you would then be able to evaluate the integral, again, either by the fundamental theorem of calculus or with your calculator. But how do you set that integral up? That's what we're going to explore in all of the different examples today. All right, so here is the official formula for the area between two curves. If you would like to pause that to write it down, that would probably be a good thing. The formula is down here. This is just a bunch of other stuff that you should know about the formula. For example, the function should be continuous over an interval where one function's values are greater than or equal to the other function's values for all x in that interval. Okay, or we could say that there's one clear upper curve and one clear lower curve. And in this formula, it is always the upper curve minus the lower curve to find the area between the two. Okay, before we move on to the rest of the examples in the notes, I would like to mention that there are some practical examples out there to finding area between two curves. The ones that I thought were actually the most interesting were ones in economics, and I believe that this is clickable. Yes, so this takes you to a website where it explains area between two curves, but also some cool applications. And if you're one of my students, I will link this and put it in Google Classroom. So if you're interested a little bit more in those practical examples, you can see them there. Okay, but now let's move on to the rest of the examples in the notes. Okay, what we're going to do is we're going to take baby steps here. We're going to start with a picture given to us, the interval given to us. So basically, you just got to set it up. And I'm even going to just go straight to the calculator to get some of our values just to make this video a little bit short. Okay. But then I'm going to start to pull back and not give you as much information, and you're going to have to find some more pieces of information to set up the integral that you need. Okay, but let's start with, again, baby steps, something simple here. If I give you this picture and I say, find the area enclosed by the given functions, okay, that would be this region. All you need to know is that you are setting up an integral from this value to this value. Now, you could confirm by graphing these for yourself, but I'll just tell you this is from -1 to 1, 2. Of the upper curve minus the lower, upper function minus lower function. So that would be 2 minus x squared minus -x. That really becomes a plus x right there, right? I mean, if you want to write it out as minus -x, you can, but that is just going to change to a plus right there. Okay, and again from here, just to save us some time, you could do an antiderivative, plug in upper minus plug in lower, or we could just do this if I'm letting you use your calculator. Comma x, comma -1, comma 2. And there it is. The answer is 4.5 or 9/2. That's it. That's as easy as it gets, okay? Pretty easy, I assume. But like I said, as I keep going, I'm not going to give you as much. So in example 3, not only do I not give you a picture, but I also, because I'm not giving you the picture, I'm not giving you the points of intersection that would be for the region that the two functions enclose. So we're just to find the area enclosed by the parabola y equals -x squared and the line y equals x minus 6. So again, just to save some time, I'm going to grab our calculator and graph both of those functions to get a quick graph. Okay, this is what we're working with, and you can definitely see on the calculator that there is this region right here that is enclosed by this parabola and this line. So that's the area that we're finding. We're trying to find the area of that region. Okay, so we can definitely see from that graph pretty easily that the parabola, -x squared, is the upper function. X minus 6, the line, is the lower function. So we can set up our integral of -x squared minus, okay, be careful when you have more than one term that you're subtracting. You need to either write an extra set of parentheses around those two terms, okay, or you could distribute right away and say that's minus x plus 6. Okay, so little things to, make sure you know about algebra here. But the other big thing here is that we don't know the points of intersection, do we? We need the limits of integration, and we're going to find those from the points of intersection here. Okay, if you were not using a graphing calculator, you would just set these functions equal to each other. Find the POIs, points of intersection, not points of inflection, points of intersection. And that would come from solving the equation negative x squared equals x minus 6, or 0 equals x squared plus x minus 6. That could be factored pretty easily. What would it be? Plus 3 minus 2. And so x equals negative 3 or x equals 2 are your limits of integration, the points of intersection and the limits of integration. Okay, again, if I am letting you use your calculator, you could just calculate those points of intersection one at a time, and you can see them right there. Make sure you're taking the x coordinates from those values. Okay, from here, we have everything we need to finish and get the answer, right? Let's just let the calculator do the rest of the work. I am going to do another math 9, negative x squared minus x plus 6, comma x, comma negative 3, comma 2 gets me an answer of 20.83 repeating, or 125 over 6. Square units, I typically leave the units off. I don't just write square units when there's none apparent. All right, so again, I didn't give you as much information here, but still pretty simple stuff, right? You just needed to graph it yourself and find the points of intersection for the limits of integration. Okay, now take a look at example 4. Find the area enclosed by the graphs of y equals 2 cosine of x and y equals x squared minus 1. So again, I'm giving you two functions, no graph and no interval. So let's take a look at this in the graphing calculator. And this time, since it is one of the functions is a trig function, I think I'm going to do a zoom 7 viewing window. There's 2 cosine x, beautiful, and there's x squared minus 1. Okay, so we are finding the area of this region, and we can definitely see that the cosine curve is the upper function and the parabola is the lower, right? So we can set up our integral as 2 cosine x minus x squared plus 1, if we distribute the minus to both of those terms, dx. So still not bad. Okay, but we need those limits of integration, which we will get from the points of intersection. And here's what I want you to see in the calculator with these. Okay, this is definitely a calculator active problem. The points of intersection are not rational numbers. Okay, they're not easy numbers to work with. And so what I'm going to do, I'm going to show you how to do storing in your calculator so that you can actually use those exact values instead of approximations. Okay. What we can do is we can take this x equals negative 1.265424, I'm sure there's more numbers to it, and we can quit out of the graph menu and, come back to a home screen. And then that number that we're working with is actually currently stored in the variable x. Watch this. If you just click x and hit enter, that number is there. Now the problem is that we need to calculate another point of intersection. We need another x value. And so what I'm going to do is I'm going to take this x and I'm going to store it. There is a button above the on button on these calculators that says STO with an arrow. When you click it, you just get an arrow. And I'm going to store it in the letter A. I hit alpha math to get the letter A. I hit enter, and that now tells me that this number is now stored in A. Okay, and I can use that letter A throughout any of my calculations. I could take 2 times A. I wouldn't want to do that in this case. 2 times A. And it takes that number times 2. Okay, again, I don't know why I would want to do that, but you get the idea. That number is now in A, and I can use it in calculations. Okay, so what I'm actually going to do is I'm just going to call this A for right now, and I am going to sort of do a little sketch just to be clear here in my work, what is A? Okay, that's the, what we're working with here, right? And this point right here is A. Now we're going to do the same thing for the other limit, the upper limit of integration. Let's calculate the point of intersection with the right endpoint. Enter, enter, enter. And it's actually just the positive version. Okay, could actually call that the opposite of A, but let's go ahead and call it B. So that number that I just calculated now, positive 1.26 and so on, is stored in X, but let's take it and store it in B. Okay, so now anytime I bring up the letter B, I'm using that number. So we're going to call this point of intersection B, and we'll put it right there. Okay, now watch this. Math 9, 2 cosine of x minus x squared plus 1, comma x, comma A, comma B gets me the correct answer, 4.995. So I didn't need to do internal rounding with my limits of integration because I used my calculator and I stored those exact values in my calculator. Okay, so finally, on the last page of the examples that we have for this lesson, you're going to see just a couple of other little things that I want you to keep in mind when you are working with these types of problems. Okay, example 5 is going to seem a little bit tricky, but once you practice it a little bit, it's not too bad. What we're to do here is find the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. Okay, so I don't know if a red flag is popping up in your mind right now, but notice that this second equation is a little bit of a red flag here because it is not written as a function of x. It's written as a function of y. X equals y squared minus 2. Okay, if we want to see that in the graphing calculator, we actually need to solve it for y. That would mean adding 2 and square rooting. And if we would want to fully see the curve, okay, it's going to not actually be a function of x anymore because we will have a plus or minus, a plinus with that root. Okay, and it looks like this. What is it? X plus 2. We add the 2, we square root, we put that plinus with the square root if we want to see the full curve. Okay, and maybe I should go to Desmos to show you that. So originally it was x equals y squared minus 2, and so that's the curve that we should be seeing. That's x equals y squared minus 2. How do we get that here? You can't type x equals y squared minus 2, right? But what you can do is you can type in the square root of x plus 2. Take a look at that. That's just part of it. That's the positive root part, right? And then go into y2 and type in negative root x plus 2. And that gives you the full curve of x equals y squared minus 2. Okay, finally, we for our third function now in our calculator, we're going to need x cubed. All right, so we're finding the area of this region. I'm going to do a zoom box and just draw a box around it to make it a little bit more apparent. And it's up to you if on your notes, if you want to draw this. It's usually a good thing for students to draw out so that if they go back and look at it later on, they can say, oh yeah, this is what the graph looked like, instead of having to bring it back up on their calculator again. Okay. The weird thing about this example is that sometimes when you do upper minus lower, you actually have to do it more than once, okay, if you know there's like a change in what's upper and what's lower. Okay, and here's what I mean. From, I don't know if that's -1, I think that's -1 to 2, I believe that is. Yes, the positive root is above the cubed graph, and so doing upper minus lower will work. But in this little region over here, there's this weird thing happening where the positive root is upper and the negative root is lower. So you would have to actually set up 2 integrals to get the area. Okay, that's if you integrate with respect to x. But actually, there's this thing that we can do where we can say, you know what? If we would take this graph, okay, I'm just going to try this as a screenshot and see if it works. Copy it, paste. If we take this graph, yes, this will work. Watch this. And we rotate it like that. So the x-axis is up and down, and the y-axis is side to side. Hey, then there is definitely a very clear upper curve right here and lower curve right here. Now you might be saying, but this is still a positive root on this side and a negative root on that side. Well, it's not a plus or minus curve if we go back to this form. X equals y squared minus 2 instead of y equals minus root x plus 2. That's just a mess to work with, okay? But again, what we're doing here is we are, instead of looking at it how we typically look at it as x, is the horizontal axis and y is the vertical axis, we're turning it like this. So the positive x's are going up in this direction. Okay, now we can see that this graph is on the top and this graph is on the bottom. And this is called integrating with respect to y. Integrating with respect to y. Okay, so let me show you what I mean. I'm going to go back to this equation, x equals y squared minus 2. And I know that that is my lower function when I'm looking at the graph like this. I want to take this equation then, and I'm going to solve for x. Cube root both sides to do that. And when I'm looking at my graph turned like this is the upper function. And so now I could set up my integral as the cube root of y minus y squared minus 2 dy. And again, this is called integrating with respect to y. We're going to put a smiley face because this is extremely fun. Okay, so we're almost done here. It was a lot of explaining to get to this point. Okay, not all these problems take this long, but I had to explain what we were doing to set it up the way we were. All right, the only other thing we need is what? We need the limits of integration, right? We need our a and our b. So the only other thing you need to keep in mind is that because you are now integrating with respect to y, you are looking for the y coordinates of the points of intersection. Let's go ahead back to the calculator like this, and let's calculate those points of intersection. Now just be careful. Let's see, for the left point of intersection, we want to be on the negative root. Calculate, option 5. It moved it. We want to be on the negative root and the cubed graph. Yes, to get that point of intersection. Okay, the x and the y are the same, but I'm taking -1 from the y coordinate. The y coordinate of this point of intersection is -1. That's right here. And so that's my lower limit, okay, because that's the lower y value. I know it's weird, the orientation of it is a little bit weird, but just take the lower number right here. All right, and then I'm going to do second trace, option number 5 again, and I want to be on the positive root, and I want to be on, I need to move, I want to be on the cubed graph to find that point of intersection. Yes, let's do that. Okay, look at this one. Whoops, not x coordinate. Y coordinate is not a nice number. It's 1.79. I mean, 1.793. If you want to write that, go ahead, and I'm sure using 1.793 rounded is not going to throw off your answer that much. But I just want to remind you that you could use the letter Y, I'm pretty sure. Let's try it. Yep. You can use the letter Y in your calculations instead. Look, did you see how excited I was? I was like, yeah, you can. All right. And, it'll work out. Or, I'm going to be typing Math 9 with Y's. So maybe I want to store that somewhere. I don't know. Let's try it without storing it. I'm just going to use Y twice. This might seem a little bit weird in our Math 9, but let's try it out. Here's what we're going to do. Math 9, we're going to bring up a cube root of y. Alpha 1 gives you your y. Minus y squared plus 2. Let's distribute that so we don't need too many more parentheses here. Minus y squared plus 2, comma y, not comma x, but comma y, comma -1, comma, you can either use 1.793, or I'm just going to be dangerous here and say, let's just try a y right there and see what happens. The calculator's like, no, I don't know what you're doing right now. Oh my gosh, the suspense. I'm going to pause my video right now. It worked. Oh. It worked. Okay, I paused the video. I waited for a moment. I'm like, oh, I just messed it up. No, it worked out just fine. There's the answer. 4.215 approximately is the area between these two curves. Woo! Okay, so sometimes that happens that whenever you are looking at the graph, let's go back to the graph one more time, and it almost seems like the curves are lying on the left and the right instead of top and bottom. You can do that little turny thing like this and integrate with respect to y. Write everything as x equals a function of y. Okay, solve for the x in each equation. Use the y coordinates as your limits of integration, and it should work out just fine. Okay, finally, the last example. This one's actually hopefully going to seem pretty easy compared to what we just did. It says, find the area of the region enclosed by y equals secant squared x and y equals sine of x on the interval from 0 to pi over 4. Look at this. We're going right back to me giving you everything. I give you a picture. It's a little bit of a weird picture, I admit. I think it's actually supposed to be like this is blue, like all under the secant squared curve is blue, and under the sine of x curve is red. And when you mix the blue and the red, you get purple. And that's the part that you're trying to take out. I think that's what that color system is trying to show. I didn't do it. Somebody else did. And I just stole it. Other than that, I give you everything. And what we're doing here is we're finding the area of this, this region right in here. Okay, what I want to do with this one is I want to go back to the fundamental theorem of calculus one more time and show you that instead of using Math 9, this could be one where you need to do it without a calculator. All right, and so let's just do one more of those to finish up. I can clearly see that my upper curve is secant squared. My lower curve is sine. And I am going from 0 to pi over 4. Okay, but from here, let's use the fundamental theorem of calculus one more time. Remember, you get an antiderivative, and then you plug in the upper limit minus plug in the lower limit, just to show that we can still do that. The antiderivative of secant squared is tangent. Negative sign is the derivative of cosine, right? So this is plus cosine. Evaluate from 0 to pi over 4. That means tangent of pi over 4 plus cosine of pi over 4 minus tangent of 0 plus cosine of 0. Tangent of pi over 4 is 1. That's why I made that weird face. I'm like, do you know that? Tangent of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2. Minus tangent of 0 is 0. Cosine of 0 is not 0, though. It's 1. So our final answer is root 2 over 2. Done. Yay! Okay, everybody. As usual, I hope this video was helpful. Bye.